potential difference. In this video, we'll be introducing moving electric charges, potential difference, and electron volts. First, let's consider an object in Earth's gravitational field. When we release the object, it falls and accelerates due to gravity, and as it gets faster, it gains kinetic energy. Now, to account for this kinetic energy, as energy cannot be created or destroyed, we assume that the object had a potential energy due to its position in the field. And it is this potential energy that was converted to kinetic energy when the object was released. So now let's look at a situation where we have an electric field. So consider a charge Q, as in the diagram on the right hand side, and we're going to place a positive test charge at point B. If this positive test charge was released, it would go in the direction of the field lines and it would accelerate away from the charge, gaining kinetic energy. So to account for this kinetic energy, we say that the charge must have had potential energy due to its position in the field, and we call this electric potential energy. So let's look at a few examples of electric charges in electric fields and see the change in kinetic and potential energy in these situations. So the first one at the top, we've got a negative charge plate, and here there's a positive charge that is being moved towards the plate. Now, because it's positive and negative, there's an attraction force, and this positive charge will accelerate towards the plate. So this is a similar situation where you have a mass in a gravitational field and it falls towards the Earth. The kinetic energy is increased and the potential energy is decreased. If we have a scenario where we have a negative charge and it's pulled towards the negative plate, there's a potential energy that is increased, and it's similar to the situation where you have a mass in gravity's field and you raise it higher in the field, further away from the Earth. Another example is when we've got a positive charge and we're pulling it towards a positive plate. Naturally wants to repel. So what we're doing by bringing it closer is increasing the potential difference. And the final scenario is when we've got a negative charge and we're pulling it towards a positive plate. It's going to get kinetic energy and lose that potential energy. Now, by definition, the electric potential difference between 2 points in a field is the work done by moving a unit test charge between those 2 points. Okay? And then when we talk about work, we can consider work to be the same as energy. And using this definition, we can come up with the equation that's on the screen. Another word for electric potential difference is voltage. So if we look at it another way, if a charge moves in the opposite direction to where the force of the field is exerted on it, it is gaining energy and work is done on the charge. And rearranging the previous equation, we get the one on the screen. By the law of conservation of energy, energy cannot be created or destroyed. So the energy is transformed into potential energy in this case. Now, if a charge moves in the direction of the force of the field freely, it gains kinetic energy. And this comes from the transformation from potential energy to kinetic energy. Now, when we're discussing and investigating electric energy, a lot of the time the energy levels that we are concerned about are very, very small. A joule, for example, is the standard unit for energy. However, 1 joule is a very large unit when we're considering the energy related to electrons and stuff like that. So when we're concerned about energy levels related to small particles, it is more convenient for us to talk about electron volts. Now, by definition, 1 electron volt is the work done on an electron when it moves through a potential difference of 1 volt. A few examples of what this means. If an electron moves through a potential difference of 300 volts, the change in potential energy is 300 electron volts. If an alpha particle, now that has a charge of positive 2, if that moves through a potential difference of 400 volts, the energy is per charge, and because we've got a plus 2, the change in potential energy is 2 times the 400 volts, being 800 electron volts. Now, the work done can be calculated in joules and then converted to electron volts. So 1 electron volt is the equivalent of the charge on an electron, being 1.6 times 10 to the negative 19 joules. And the best way to remember this is that in joules, the energy levels are very small and you have a very small number. And the point of electron volts is for convenience. So when you do the conversion, The electron volt should be a nicer number, a large number, in comparison to when you write it in joules. If this positive particle was pulled towards the positive plate and against the field, is kinetic or potential energy increased? And additionally, if it moves through 300 volts, what's the energy that is transformed?